Welcome, my dear students, to another topic of Chapter 12 Thermodynamics, and the topic is heat engines. Yes, heat engines. You might have already seen many heat engines, but you might not be knowing that these are known as heat engines, like diesel engine, petrol engine, kerosene engine, and even the steam engine that you might have seen in the train. These are all heat engines. So, dear, we are going to study here heat engines. Heat engine is a device in which system undergo a cyclic process and converts heat into work, or it converts heat into mechanical energy. See why these heat engines are used. It is used to convert the heat into work, or say heat into mechanical energy. And for that the system undergoes through a cyclic process in a device, and that device is known as heat engine. This heat engine consists of working substance like petrol, diesel, kerosene, steam, air, etc. These are all known as working substance of the engine, and they play a role of system in the engine. One of the heat engine is shown here in this picture. This is a 4-cylinder petrol engine. You can see these are all the pistons, right? And here the combustion of the fuel takes place, and due to that heat is produced, and due to that heat this piston will travel downside, and due to that this crankshaft will rotate and produces mechanical energy, or say work. So heat is converted into mechanical energy, or say into work. So that is done by such type of heat engine. In this type of engine, working substance goes through several processes and completes a cycle. See, this is important, that the engine completes a cycle. It's a cyclic process inside this engine. In some process, this working substance absorbs Q1 heat from the hot reservoir at T1 temperature. In other process, this working substance releases Q2 heat in cold reservoir at T2 temperature. This is what you have to remember, that the working substance absorbs Q1 heat and releases Q2 heat. Obviously, the reservoir from which it absorbs heat is at high temperature, and so it is known as hot reservoir, and the reservoir in which it releases the heat is having low temperature, that's why it is known as cold reservoir at T2 temperature. Also, a work W is transferred by the system to the surrounding in each cycle. Now, this is the basic need of the engine, right? We need work from the engine. That's why in each cycle the system transfers work by some mechanism, whatever it is, to the surrounding. If you remember, in the previous picture I have shown a shaft which was connected with pistons. This shaft is the medium by which the system transfers work to the surrounding. Alright. Now, here is a schematic diagram of a heat engine. You can see here is shown the working substance, that means the main system, and here is a hot reservoir at temperature T1, and here is a cold reservoir at temperature T2. Obviously T1 is larger than T2. And now you can see that working substance absorbs Q1 heat from the hot reservoir and releases Q2 heat in the cold reservoir. Meanwhile, it also gives a work W. So we can say that working substance absorbs Q1 heat and divided into two parts. One part is Q2 heat and another part is W work. So from the conservation of energy we can say that Q1 will be equal to Q2 plus W. And so we can also write work W is Q1 minus Q2. Let us name it like equation 1. Now the ratio of work produced and the heat absorbed is known as efficiency of engine. See, efficiency is always ratio of output upon input, right? Now, what is the output of any heat engine? The output is obviously work. And what is the input of the heat engine? The heat which is absorbed, right? So the ratio of work and the heat absorbed is known as efficiency, which is denoted by this symbol. This symbol is known as eta. So efficiency eta is work W upon heat absorbed Q1. But from the equation 1 we know that W is Q1 minus Q2. So this is Q1 minus Q2 divided by Q1. So Q1 will be cancelled out and here you will get Q2 upon Q1. That's why the equation of eta becomes now 1 minus Q2 upon Q1. Eta is equal to 1 minus Q2 upon Q1. Now in this equation it is quite clear that if Q2 is 0, then this whole term will become 0 and so eta will become 1. When eta is 1, it shows 100% efficiency. 1 means 100% here. Alright. So if Q2 is 0, then eta will be 1. That means the engine will have 100% efficiency. Means engine will convert all the heat absorbed into work. The heat Q1 which is absorbed will be converted 100% into work W. But in practice Q2 will never be 0 and so eta is equal to 1 is also not possible. That means 100% efficiency is not possible. Understood? See, the equation shows that if Q2 is 0 then efficiency will be 1, that means it will be 100%. But our experience says that even if you reduce the losses to be 0, then also 100% conversion of heat into work is not going to happen ever. Why it is so? Because that is the principle of nature, right? This principle of nature is known as second law of thermodynamics, which we will study in next coming topics. Now let us see types of heat engine. See, by the mechanism of conversion of heat to work, two different type of engines are made. The first one is internal combustion engine. Here in internal combustion engine, the combustion of fuel takes place inside the engine, like petrol engine, diesel engine, CNG engine, kerosene engine. These are all basically internal combustion engine because here the combustion is taking place inside the engine. See this figure here. In the first figure you can see that the piston is moving upside. So it is compressing a mixture of vapor of petrol or diesel and air inside this cavity. When this piston reaches the top point, the spark plug produces a spark which explodes the mixture of petrol and air. This explosion is shown here. Now due to this explosion, the piston will now travel to downward direction, right? So that way work is gained from the heat produced by the combustion of this fuel inside this engine. That's why this type of engine is known as internal combustion engine. The second type is external combustion engine. Here the combustion of fuel takes place outside of the engine like steam engine. See, in such type of engine, the combustion is taking place not inside but outside of the engine. For that, see this figure here. This is a figure of steam engine. You can see here the combustion of coal is taking place and due to this combustion, large amount of heat is produced which heats up the boiler which is filled with water. Now due to the boiling, steam is produced and this steam with high pressure pushes this piston outside and so work is achieved. Now here you can understand that this is the basic engine, right? But the combustion is taking place outside the engine and that's why this type of engine is known as external combustion engine. Obviously the efficiency of external combustion engine is less than the internal combustion engine and that's why you might have noticed that nowadays the steam engines are just stopped. Government is not allowing to use this type of steam engine anymore. Now let us see topic 12.10, refrigerators and heat pump. You might have already heard about refrigerators, which we call generally as fridge, and Heat pumps are such devices that provides heat, especially in cold area. It provides heat in any chamber, in any room, wherever you require. So that is known as heat pump. Let us see both of them. Refrigerator is the reverse machine of heat engine. This you will understand when we will study this schematic diagram. Okay, now here external work is done on the working substance, and so the working substance extracts heat Q2 from the cold reservoir at temperature T2 and releases heat Q1 in the hot reservoir at temperature T1. Interesting. See, in heat engine, we were giving some heat, out of which an amount of that heat was converted into work and the rest of heat was released in the atmosphere, right? But here the things are absolutely opposite. Here we are not getting any work, rather we have to do some work on the working substance. So the working substance will extract heat Q2 from the cold reservoir and it will release heat Q1 in the hot reservoir. It will extract heat from the cold reservoir and release heat in the hot reservoir. Remember this thing. So now you can see how this machine is absolutely reverse than the heat engine. Here, as we keep on doing external work on the working substance, it will keep on absorbing heat from the cold reservoir and releasing heat in the hot reservoir. So the cold reservoir will become more and more cold and the hot reservoir will become more and more hot. Now in refrigerator, because we have to cool down the things, that's why the things are kept in cold reservoir. And obviously in heat pump we have to heat up the things, so we have to put the things in hot reservoir. Let us see. In household refrigerator, the inside chamber is the cold reservoir and the outside surrounding of the body is the hot reservoir. Let me explain you this. Here you can see a fridge and this is the internal chamber which we have to cool, and this is the outer body which is in contact with the atmosphere, and that's why it is the hot reservoir. The inside portion is the cold reservoir and the outside body and the surrounding, everything is hot reservoir. You might have observed this thing in your home fridge also, that the outer body of the fridge is always hot. When the fridge is running, the inner body will be cold but the outer body will be hot. Now let us understand heat pump. Heat pump is same as the refrigerator, but it is used to heat the chamber or the room. So the cold reservoir is the surrounding, that means the outer part, and the hot reservoir is the inner chamber or the room itself. So in heat pump what is done, that the hot reservoir is the room or the chamber which has to be heated up, and the cold reservoir is the outer surrounding which is at a low temperature. Alright, in refrigerator the working substance goes through several steps. The steps are here. First, sudden expansion of gas from high pressure to low pressure cools the gas. First of all, what is done? The gas is at high pressure and it is suddenly released. So due to the sudden expansion, the temperature of that gas will reduce. That means the gas will cool down to low temperature. Now second, this cold gas absorbs heat from the chamber. Now this cold gas is passed through the chamber of the refrigerator inside, and so it absorbs the heat from the chamber. Third, by external work, the gas is again compressed to high pressure, which increases the temperature of the gas. Now, here you might be aware that every fridge is having one sort of compressor. This compressor is to compress the gas, right? So, compressing gas is an external work. So, by this external work, means by compressing the gas at high pressure, the temperature of the gas increases. Obviously, when we compress the gas, the temperature will increase, and that's why the temperature of gas increases. Fourth, the heat is now released from the gas into the surrounding. Now, by heat sink or some sort of fan or any other type of mechanism, the heat is released from the gas into surrounding. The same what I was talking about, that the body of the refrigerator becomes hot. Why? Because the body is behaving as a heat sink right now. So it is absorbing the heat from the gas and it is releasing the gas into surrounding. Alright. This brings the gas to its initial state again, and this completes one cycle. See, after this fourth step, the gas is again compressed and the heat is already released from the gas. Alright. So it is again in the initial condition. Now again the first step will be repeated, and so the another cycle will continue. Alright. This way, as we have seen in the second step, that the cold gas absorb heat from the chamber, and as we have seen in the fourth step, that the heat is released from the gas to the surrounding. So continuously heat will be absorbed from the chamber and will be released in the surrounding. That's why the temperature of chamber will decrease on and the temperature of the surrounding will increase on and on. Okay, now let's move forward. From the schematic diagram of refrigerator, we can see that Q1 is equal to Q2 plus W, where W is the external work done on the substance, Q2 is the heat absorbed from the cold reservoir, and Q1 is the heat released in the hot reservoir. So from this we can write W is equal to Q1 minus Q2. You can see W is equal to Q1 minus Q2 is the same equation that we were getting in the heat engine as well. Now, an important parameter for refrigerator and the heat pump. Here obviously efficiency is not a parameter, but coefficient of performance alpha is a parameter. Now coefficient of performance of refrigerator is alpha is equal to Q2 upon W. Mind well, Q2 is the heat absorbed from the cold reservoir upon W is the external work done on the substance. Now obviously W is Q1 minus Q2, so again alpha will be Q2 upon Q1 minus Q2. But the coefficient of performance alpha for heat pump can be written as alpha is equal to Q1 upon W. Mind well, in refrigerator it is Q2 upon W, but in heat pump it is Q1 upon W, where Q1 is the heat released in the hot reservoir. Again here also W can be written as Q1 minus Q2, so the equation becomes alpha is equal to Q1 upon Q1 minus Q2. From both of this equation we can say that if somehow the work W is 0, then alpha will become infinite, right? Keeping this point in our mind, let's move forward. As the heat engine cannot convert heat fully into work, so the efficiency eta cannot be 1. We know that heat engine cannot have 100% efficiency. That means it cannot convert all the heat into work. That you know already. The same way, refrigerator or heat pump cannot transfer heat from cold reservoir to hot reservoir unless we do some external work. So alpha cannot be infinite. See, in case of refrigerator or say heat pump, it is very much required that you do some external work on the working substance. Unless and until you don't do some external work, it is not possible to transfer heat from cold reservoir to hot reservoir, because it's a very natural phenomena that heat always travels naturally from hot reservoir to cold reservoir. Yes or no? Heat always transfer from hot reservoir to cold reservoir. So here, without doing any external work, it is not possible that heat will transfer from cold reservoir to hot reservoir. That means work cannot be 0. In case of refrigerator and heat pump, work cannot be 0. And because work cannot be 0, then from both of this equation we can say that alpha cannot be infinite, because if work is 0 then only alpha can be infinite. So here it is mentioned that alpha cannot be infinite. So finally we have to remember that in case of heat engine the efficiency eta cannot be 1, that means it cannot be 100%. The same way in case of refrigerator and heat pump, the performance coefficient or say coefficient of performance alpha cannot be infinite. Alright. And so herewith students, I complete this lecture today, and as I always say, please note down all of such type of equations which I have bracket, that are all very important equations and will be useful in MCQ and numericals. Also, as I always do, I have made a PDF of all the writing work that I have done today, and that PDF is kept in description box. You can download it and can write down from the PDF directly. Alright. So here I am signing off, Anshuman Baldania.